single sideband signal so that you didn't splatter. I don't know where my two-tone generator is. It's somewhere, but I don't know where. So without further ado, I'll introduce Richard, and he will talk to you about the performance of a two-tone generator. Richard.
Cool, thank you. And I'm going to be talking to you this evening about a two-tone generator project I've recently completed. You're going to have to excuse my croaky voice / throat because I have a bit of a cold or something, and so yeah, struggling a little bit to speak, but bear with me. Okay, so just before we get started, I thought we'd have a bit of a quick review of the agenda, some of the items I'm going to speak about this evening. So first thing is the motivation for the project. Why did I build this device? A little bit around what a two-tone generator is, why we need one, some requirements for the generator. I'm going to talk a little bit about the architecture, and then I'm going to get into some of the details of the blocks within the generator. So the direct digital synthesis block, MicroPython board, summing amplifier board, and then putting it all together, and then there'll be a little bit of time at the end for some questions. Okay, so motivation for the project. Okay, so I've got a Yaesu FT, excuse me, 818 transceiver. Excuse me, according to the manual, it can produce about 6 watts or so on single sideband CWRFM, and maybe around 2 watts on AM, and that's at about 13.8 volts. So, you know, if the voltage is lower, then the output power will drop a little bit too. But I'm looking to build a 6-metre amplifier for this radio. I've currently got a 2-metre amplifier, but I wanted to build a 6-metre amplifier as well. Something to produce, excuse me, something to produce in the order of about 80 or 100 watts. But before I designed that amplifier, I really wanted to check the linearity of the FT818 at various output powers and at various microphone drive levels. And the reason for this is that it's going to inform some of the specifications for the amplifier, such as the amplifier's gain and the level required to achieve particular linearity. Thank you very much, Peter. So, and then once I've built the, built the amplifier, I'm hoping to check the linearity of the combination of the amplifier and my radio together. So that was what the driver was for this project. Okay, next thing, what is a two-tone generator? I thought I'd talk a little bit about this because not everyone may know what it is or what it's for. So I'm going to go into a little bit of detail about that. So basically a two-tone generator is a device that produces 2 audio tones and adds them together. And there's a block diagram there. You can see of a two-tone generator. So in this case, I've got a 800 hertz tone and an 1800 hertz tone. And then I've got a summing block here, or adding block, which adds the signals together, and then an amplifier here to control the gain of the level, or to control the gain or the level of the audio going into the microphone input of a radio. It's designed to be used in conjunction with either a spectrum analyzer or an oscilloscope, and I'll show you a test setup now. So that is a kind of a test setup I made up. So radio, RF output of the radio goes into a power attenuator, and then that goes into a spectrum analyzer or a cathode ray oscilloscope. Okay, so this is looking at the time domain, and this is looking at the frequency domain. Now, I don't have a spectrum analyzer that looks like this at home. I'd love to have one, but I don't, just in case anyone's getting envious and wondering what's going on. It just came from a bit of Googling. So I thought it would be worth delving into a little bit why we care about linearity. Why does it matter? Well, it matters because basically it's in relation to modulation. So I'm just going to go into a little bit of detail about some of this modulation, not too deep though. So if we think about amplitude modulation, or AM, or ancient modulation, as it's sometimes called, the information's carried on the envelope of the wave. So you can see here, goes up and down with your voice, okay? Single sideband, on the other hand, carries information both in amplitude and in phase. You can see here, frequency's changing a bit, but so is the amplitude too. And then FM, we carry the information in frequency and phase only. The amplitude stays constant. Okay, and this is related in certain ways to amplifiers as well, or linearity is related to amplifiers as well. So you might have heard Class A, B, Class B, Class C, etc. That's beyond the scope a little bit of this presentation, but if you're interested in that, you can always do some Googling and have a look at that. So for modulation that carries information in the amplitude, such as AM and SSB, if the amplifier is not linear, the information is going to get corrupted. Okay, so what does that really mean? I say it gets corrupted. Well, basically, there's two effects that can happen. Firstly, you can get distortion of the signal, so reduced clarity. So if I'm speaking to someone and it's too distorted, the person at the other end who's trying to listen will struggle to hear, even if the signal's strong. Okay, so I'm impacting myself and the other person. But probably the bigger impact, or the one that can be an annoyance to our fellow operators, is spreading of the signal, or splatter. And that impacts, other users of the band. Okay, so on VHF and above, it's probably a bit less of an issue in a sense because the bands aren't as crowded. On HF, I think it would be, far more of an issue where the bands are a lot more crowded. So obviously, neither of those is desirable. We want to make sure the person we're talking to can hear us, but we also want to make sure we're not interfering with others when using our band or our spectrum, in a way that's considerate, really, for other people. So really the aim is to try and keep distortion of your transmitter to a minimum. All transmitters have distortion to some degree, but we want to keep it, minimum, so as we're, operating in a way that's, not going to upset other people. So, some requirements for this device, this two-tone generator. So there is 3 key requirements that I wanted to look at or consider before I started building it. First one was the tone frequencies. Second one is the output level. And the third one is distortion. So we'll talk about the tone frequencies first. So there's many tone frequencies that have been used over the years in various projects, such as 800 Hertz and 1800 Hertz, 1000 and 1600, 707 and so on. And there's some references at the back that talk about some of those oscillation frequencies. Really the key requirements around those frequencies are they need to be in the audio band, so that, in the 300 Hertz to 3 kilohertz sort of band where your voice normally occupies. And they should not be harmonically related. And this is because we're trying to measure intermodulation distortion rather than harmonic distortion. And I'll go into what that means a bit later on, so don't worry if it's not particularly clear, that distinction. I decided to choose 800 Hertz and 1800 Hertz. There was no, particular reason. It just sounded like nice round numbers, so I thought I'll go with those. So the second requirement was the output level of this two-tone generator. So the peak audio level really needs to be at about the same level as the peak of your voice when you're speaking into a microphone. And I needed to measure this level. I had no idea when I speak into which I have here, the 818 microphone, I had no idea what the level was going into the radio. I knew it would be fairly small, but I didn't know what small was. So I needed to measure this. Now I thought about creating a little patch lead to go between a microphone connector and then a connector on the radio. And I thought maybe I can just use an RJ45 plug and get on the back of that. But then I thought, as soon as I do that and I get my oscilloscope probe and try and measure it, for sure I'm going to end up shorting pins and potentially blowing up something on my radio. So I thought, it's just not worth it. I'm going to build a breakout board. So that's a picture of the breakout board, and it's literally just straight through connections, and I've got it here. I'll pass it around. There we go. It's literally just a RJ45 patch cable, network cable that I cut, soldered onto the board, and then just put a RJ45 socket. And then onto that board, I just soldered on some keystone test points. They're these ones here, really good. You can get your crow probe into the end of them, or multimeter tip, whatever. And that allowed me to measure the level using the oscilloscope probe directly on this board. So I had a short, just use a tip, and then I also had a bit of wire here wrapped around the ground part of the probe. And the reason I haven't used a big long clip lead here, which is often connected to the probes, is just because of noise level. I'm trying to measure very small signals, so I want to keep this loop really small, very short connections. And that worked pretty well. And I just designed this circuit board using Altium Designer, which I have access to, and had it made using JLC PCB. So cost in the order of about $3, I think, to get these boards made, and probably cost about $20 in postage, but that's okay. It's still pretty cheap. All right, and that's a picture of the schematic. Very boring, really. Just straight through connections with some test points. Nothing much to it. Okay, so once I did that, I was able to measure the levels of my voice. So I was sitting in my shack, just making funny noises to the great amusement of my kids and wife. And anyway, I found after a bit of messing about and testing, I used the persistence facility on the oscilloscope. I found that I could produce about 16 millivolts peak to peak. It was roughly the level going into the radio, so it's pretty small. And a calibrated whistle was about 20 millivolts, so a bit bigger, but normal speaking voice about 16 millivolts. So that was my, that's the level really I wanted to target for the output of the two-tone generator. So, distortion or linearity of the generator. So I'm going to go into a little bit of detail here about this to understand what the requirements are for the two-tone generator. So I'm going to revisit a bit of linearity and go through perhaps a bit of modulation theory a little bit too. So just bear with me, but there is a point to all of this. So if we think about 2 meters, because I'm a VHF, UHF person, using upper sideband, if we were to inject 800 hertz and 1800 hertz into the microphone input of an ideal radio, and then we had to look at the spectrum, it would look like this. So we'd end up with 144 megs plus 800, 144 megs plus 1800. Okay, and that's the upper sideband signals. Okay. However, no radio has an output spectrum that looks like that. All radios, doesn't matter how much money you pay for them, or whether you make them, buy them, whatever, have distortion. Okay, so if we were to again get a real radio this time and inject 800 hertz and an 1800 hertz tone into the microphone input, and then have a look at the spectrum, it would actually look something like this. Okay, and you can see our blue signals here are wanted, 2 tones. You can also see distortion products here. Okay, and they're the purple ones that are called third order intermodulation products. Okay, and they're the ones that will start to cause interference in adjacent channels of your transmitter. Okay, and the other thing that's important, thinking about this spectrum, is the more non-linear your amplifier, the more compressed your amplifier is, the larger these will creep up and get higher and cause more interference. Okay, so you know, we desire to keep these as low as we can. So I mentioned before that we want to keep them as low as we can, but how low do they need to be? Well, like a lot of things in life, there's various views on this. Recently, the ARRL published in QST, I think it was, Clean Signal Initiative Group, CSI, not Crime Scene Investigator, although if your spectrum's bad enough, they might come around too. But the purpose of this is really to establish requirements for transmitters in the US. They're looking to do this, but I'm imagining they're hoping it would be adopted all around the world. But they have recommended that these distortion products are 36 decibels. That dBc means relative. It's relative to the carriers or the wanted signal up here. So they're suggesting they should be 36 decibels below wanted ones up there. Okay, and that's actually a fair bit, and I suspect even very expensive radios would probably, may not even meet that. It's pretty aggressive target. Okay, so I looked up the ARRL's test data for the FT818 for my radio. You know, they do very exhaustive testings in their lab for most new radios that come out. And I found it had a level of 30 dB. So in other words, it wasn't down at 36, it's down at 30 dB below these signals here. I was not sure what output power they did that at, I presume maximum, or what the microphone gain was set to, but just to give you an idea, that's the sort of level the FT818 was measured at. So, if we think about this a little bit more, and we have a look at and I'll just black box, just a radio, forget about what make or model it is for the minute. But if we're trying to measure intermod products, these purple ones, 36 dB down at the output, we need our two-tone audio generator to be at least 10 dB better than that, because we want to measure the radio, we don't want to measure our generator, okay? We want to measure how good the radio or what the linearity of the radio is. So I've said, right, well, we need to be at least 10 dB better than that. So this is the audio coming in, that's the RF coming out. We want to be 10 dB better, so 46 decibels below the wanted signal or the wanted audio tones. So if we summarise the requirements, just group them all together, now we've sort of got all the data. Two frequencies I want to target are 800 Hertz and 1800 Hertz. The output level we need is 16 millivolts peak to peak, and the distortion needs to be lower than minus 46 dBc or minus 46 decibels below the wanted. So that was the target. Okay, with that in mind, we can jump into having a bit of a look at the architecture. So there's a block diagram of the architecture for the device. So that the heart of the system's really these analog devices, AD9833 DDS modules. And I've got one of those producing an 800 Hertz tone and a second one producing an 1800 Hertz tone. Controlling those devices or configuring those devices with a MicroPython Pi board, and then I've got a summing amplifier board at the output, and that's got three purposes. Sums the two signals together, it balances the levels so that they're equal, and also does a final amplitude adjustment so I can hit that 16 millivolt target. Okay, so we'll start with the heart of this whole thing, the direct digital synthesis chips or modules, and I'll go into a little bit of detail about those. So in the past, these types of low distortion oscillators that you would use for two-tone testing were made using various discrete circuits, generally based around transistors or op-amps. And there's some references at the back if you'd like to have a look, mostly from AR, Amateur Radio magazine. And they worked really well, and they were fine. There's nothing wrong with those. However, with advances in technology, there's easier ways to do this now than having to sort of do it all discreetly. And the DDS chips or DDS device, direct digital synthesis device, is one of those techniques. and you've probably seen articles on using DDS devices for VFOs and things like that for rigs. So they've been used for quite a number of years now. And those devices have got quite a few advantages. One of them is the phase and frequency is programmable, which is very handy for this application. Distortion's very low, which is something also very important for this particular application. There's a low component count, so there's not lots of discrete bits, just really one IC, a couple of other things that hang off it. It's pretty straightforward. And the performance is repeatable, as everything's designed in an IC. So I could build 1 or 10,000 and I'm going to get very similar performance. Whereas with discrete analog circuits, that would, without a lot of very careful design, that wouldn't be the case. So the part I ended up using was Analog Devices AD9833, which is a low power 2.3 to 5.5 volt programmable waveform generator. It's really a relatively low frequency device, so it's perfect for this application. The low power wasn't particularly important to me, but it could be for some applications. It can generate up to 12.5 megahertz, and it's got 28-bit resolution. So that means you can tune it to within 0.1 of a hertz at 25 megahertz clock. So it's far more than I need, but it's pretty good. It can also generate sinusoidal, triangular or square wave outputs. So I definitely didn't want triangular or square wave, I wanted nice clean sine waves. So again, it's good for this application. And it can be programmed with a 3-wire SPI or serial peripheral interface, which is a standard programming bus. So easy to find things to program it with. So I've got a block diagram of the device there. I'm not going to go into all the details about it, but you can always just have a bit of a Google and look it up. And then to the left of the block diagram, you can see a board I acquired. And these are pretty cheap. I just found them on eBay. They're about $17.50 Australian plus postage. So I had a look at the price of the chip and I'm not sure I could even buy the chip on its own for that much. So it was pretty good. And there's quite a few other vendors that seem to sell boards that are very similar to these. And then once, basically I selected this, the rest of the two-tone generator was architected around this particular device. So I ordered a couple of these modules from eBay, and I thought I'd like to program them up and see what they can do. I guess there's a couple of reasons for that. One is to make sure it's really going to work how I'd like it to work. But secondly, obviously buying it off eBay, you hope the devices are genuine, but you don't really know. So I think it's good to do a bit of due diligence and check, make sure it works as you expected. So what I did is I programmed one firstly for 800 hertz, and then had a look at the output on an oscilloscope. And you can see it generates about 600 millivolts peak to peak. This is straight out of the DDS, nothing else hanging off it at this point. And then I used the fast Fourier transform function in the oscilloscope, which turns it into a spectrum analyzer essentially. And I had a look at the spectrum, and you can see here, there's the wanted 800 hertz, and you can see all the noise and thing down here, which is 56 or nearly 57 decibels down. So it's very little distortion. In fact, I can't see any distortion. This is a noise fluority oscilloscope, so it's really good. I did the same thing at 800 hertz too, because I wanted to make sure that was equally as clean, and it looks pretty good. It's about 628 millivolts peak to peak, and again, you can see the tone there, sort of the biggest noise spikes about here, and that's like 58 decibels lower than the tone. So it's a really, it's very clean. It's excellent. If I had a dedicated audio spectrum analyzer, I could probably see down a bit further and measure the actual distortion, but this was down far enough for me, so I could see that, the devices were working well. So the next part of it was, or the next thing I considered was, how do I program these devices? How do I set the frequency and other things with them? So I decided to use MicroPython. for this task, and there's a couple of reasons for that. One is I had a Pi board, which is a board you can see in that image in my junk box, so I like to reuse things in my junk box where I can. Second thing is, through work I had access to quite a few MicroPython gurus, so I knew if I came unstuck I'd be able to go and harass some people at work, and they're generally pretty friendly and like to talk about these things. So I just wanted to say, before anyone starts jumping up and down, that I've never used Arduinos and I make no claims about which one's better. So if you're using Arduinos for a project that works for you, awesome. This is just something I happen to use, but yeah, I'm not saying one's better or one's worse. It's whatever floats your boat. But I did want to go into a little bit about what MicroPython is, because you may not be aware of what it is and what it can do, and I found it, really useful for this application. So MicroPython, as it says up there, and I did copy this straight off the website, I have to say, is a lean and efficient implementation of Python 3. So you probably would have heard of Python at least, a high-level programming language, interpreted programming language, works on lots of platforms and is used, has been around for decades and is used in lots of applications. This one's a scaled back version of that, I guess is how I like to think about it. It's got lots of features, excuse me, including interactive prompt, which is very handy, and I'll show you, how we can use that in a little bit. Can do arbitrary precision integers, lists, generators, all sorts of stuff that fits into, a very small amount of code. 256K of flash, excuse me, and 16 kilobytes of RAM. And it aims to be as compatible with Python, that is the kind of Python you'd run on Windows, as much as possible, but run on a smaller platform. Now the Pi board is kind of the low-level companion board that goes with your MicroPython. You can run MicroPython on lots and lots of things, but this was one of the first boards that I was brought out to run it on. And it's just a little, small circuit board, and up the top you can see it's got a USB port, a micro B port, and an SD card interface, which I didn't use in this application. It's got some LEDs, 4 LEDs there, a couple of press buttons, and there's a microcontroller. It uses an STM32 F405. Okay, so it's certainly not the biggest STM32 microcontroller, but it's plenty powerful enough for this application. And it's got lots of pins up the sides. You can hook things up, both sides and down the bottom, and I'll show you how to utilise those in a minute. I thought I'd delve into the code just a little bit, and don't worry, there's not pages and pages of code, just this one slide. But really I wanted to illustrate how simple it was to get this thing up and going. So I'm going to go through sort of section by section. So the top bit, this very top line, imports the library for the AD9833. Now I didn't write that. I got it off GitHub from a guy called Kip Crossing. So he wrote that and just put it out there and let people grab it. So that was awesome. That's one of the reasons I wanted to use this chip. I thought, beauty, I don't have to do any work here, it's good. And then the next 2 lines, just importing some libraries that are part of MicroPython itself. I've used turned some LEDs on as I've gone through as kind of a rudimentary method of debugging. So I turn one LED on, that's all these libraries import. Next thing I do is set up the SPI bus for the first module. And then I go and set some of the parameters for this first module. So here you can see I'm setting the frequency to 800 Hertz, setting the output to sine wave, and then I send those parameters to the DDS, and that configures it. Okay, turn on another LED, shows me I've got up to this far, and then I configure the SPI bus for the second device, second DDS board, and again, I set the frequency, this time setting 1800 Hertz. I go and set a sine wave and send the data across, and then turn my last LED on. That's all it is. It's just few lines of code, and I'm outputting two clean sine waves. So it's pretty impressive. Now this board, if you grab that MicroPython board and just plug it into your laptop or computer, it just looks like a memory stick. So here it is plugged into my computer, and you can see it's got an AD983.py, that's the library I got from GitHub. It's got a boot.py, which is just built into the board, INF file readme, and the main.py. So all that code I was walking you through in the previous slide that's in that main.py file. It sits in there. Now when you power the device up, it just goes and basically executes the code within this main.py. One of the really cool things about this board is the USB interface, which allows you to plug in, as I've shown here, but it also means you can get a terminal up, and I've just used PuTTY in this case. On the terminal then I can manually send commands, okay? So instead of having to write, back in the bad old days, a command interpreter, and set up a whole lot of serial commands and program all that and then get that all working, nope. Just plug it in, get your terminal going, and away you go. I can just send commands exactly the same as when they were being executed out of this file. So it's super, and I use this for debugging. Aside from the LEDs, when I was first getting this going, I would just type it in a line at a time, and then if you got any error messages, they just appear here. I could go and debug it, get that bit going, then move on to the next section. So it worked really well. I did find a gotcha when I was programming them. I found that I have them on 2 separate SPI buses, but even with that, I found that sometimes the second one, the 1800 hertz tone generator, wouldn't start on the right frequency. Sometimes start at like 2 kilohertz or 2.1, and I had to go manually, after having run the script, get into the terminal and set it again. Now I'm not sure why that is. Excuse me. Could have been the SPI bus, because I'm carrying it over bits of wire here. It's pretty ordinary. It did the job mostly, but it's not a circuit board yet. But it also could be an issue with the driver, but I certainly wasn't about to complain about that, given the guide, just put it together and put it out there for free. So, beggars can't be choosers. I decided to just live with it and thought, well, if I have to go and set it manually, that's okay. It's not that big a deal for this application. So the final bit here, if we go on, maybe I'll just go back to this again. So we've talked about the Pi board, the 2 DDS modules. The final piece in the puzzle was the summing amplifier board. So that is the circuit for it there. So basically up the top here we've got an op amp, a inverting summing amplifier. You can see the 2 inputs here, one for the 800 hertz tone, one for the 1800 hertz tone, and it's got some low pass filtering. The second block over here just does the gain adjustment. Here you've got a pot to set the amplitude. I should have mentioned too, the summing amplifier's got a balance pot here, so this adjusts the input level of this first one to make it match the second one. Okay, I've got a PTT switch here, so I can key the radio when I want to do transmitter testing. I've got a 5-volt regulator here, and I just run 12 volts or whatever into the board and generate 5 volts for the op amps and also for the MicroPython board, and a 3.3 volt regulator. I didn't end up using this. I had this in case the TDS outputs were a bit noisy, because they're using 3.3 volts from the MicroPython board, but I found they weren't, so I didn't end up needing this. Okay, and I designed this again. This is done in Altium Designer, or ProTel as it used to be known back in the day. Cool, and there's the circuit board. Yep, and it was again sent off to JLC PCB. I think I sent it on Thursday night, and by Monday afternoon the next week, a package was sitting on my doorstep with boards in it. So it's unbelievable. Again, these only cost about $3 or $4 and probably 25 in postage, but I wanted them quickly, so I just paid the money. You can see here there's a couple of inputs. I've allowed for connectors, but didn't want to mess about, just sold wires on. So 800 hertz comes in here, 1800 hertz comes in here. This is the power that goes off to the MicroPython board. 12 volts comes in here. This pot here is for the balancing, and this is for the amplitude adjustment. Now, I stuffed up the footprint on the board, and these holes are a little bit too small, so I couldn't plug my switch in, which was a bit disappointing, but you know, one of those things. So I just put a bit of wire on and hung the switch off here. That's the PTT switch. And here's just my tail that goes to the radio. So there's a couple of connections for PTT. You can see the tracks here going to the PTT switch, and then these two are for the microphone. Output or input. So plugging it all together. So that is all test setup sitting on my bench. So PTT switch, connection to the radio, 12 volts comes in here, MicroPython board and the two DDS boards. You can see these red and black wires are the power, so there's a 3.3 volt regulator on the MicroPython board, and I'm using that to power the DDS boards, and I've got another one here, and then the white, or the two blues and the white wires are the SPI bus. So there's one bus there and a second bus comes around here. So I got it all going and then decided, right, now I really want to have a look at the output and see how well it performs. Because I knew the DDS chips work, we saw the results of that earlier, but I wanted to see how well the amplified design had worked. So I had a look firstly at the output of the summing amplifier. So if we go back up a couple of slides again. So the signal I'm about to show is here. It's the output of this summing amplifier, TP5 6. So you can see strange waveform, but that is what two tones added together looks like, unmodulated. This is still audio frequencies. So about 1.22 volts, and the oscilloscope's completely confused because I've got two audio frequencies. You can't work out what frequency it is, so don't worry about that. It's pretty meaningless. And then what I did was I again used the FFT or fast Fourier transform function in the oscilloscope, which turns it into a spectrum analyzer, and I could have a look at the spectrum. And you can see here there's 800 hertz tone and 1800 hertz tone sitting up there, which is what we expect. And then I look down here, and again, just basically noise floor. Can't even see any distortion products yet. And so I put one cursor up here, one of the tones, the other one down at the noise floor, and you can see that the distortion's very low. Okay? 55 decibels distortion or noise here is 55 decibels below these tones here. So it's very good. So pretty happy with that. Mentioned that there, and this certainly meets, you know, much better than I had my requirement of 46. So it was pretty good. I was fairly happy. Now, I then wanted to check the output when it had been, the gain had been reduced, or the amplitude had been reduced, I should say, down to the 16 millivolts. So we'll go back to the schematic again, so I can show you the point I was testing at. So the waveform I'm about to show you is here. So on the output of this stage, and this reduces the amplitude significantly down to the level that's equivalent to what my voice would be talking into my microphone. So again, I can see the two tones, fantastic. This time though, the noise is a fair bit higher. Now, it's fairly obvious it's high, even by looking at this. You can see how ragged this waveform looks. And that's because I'm trying to measure a very low signal, and the oscilloscope's not particularly sensitive. This is a fairly old oscilloscope, and it's only got about 8-bit ADC in it, so it hasn't got a huge dynamic range. So the noise is only about 35 dB down. However, I'm sure it's being limited by the oscilloscope. So I'm fairly confident if I found a better oscilloscope or dedicated audio spectrum analyzer, I think that products would be down far enough. So I didn't have anything I could measure with at the time, but I feel pretty confident it would be all right. But it's just is one of the challenges when you're trying to measure very low signals and then trying to measure distortion products of those low signals. So the next steps, I got all that done not so long ago, just in time for this presentation. I find presentations are excellent deadlines for making sure you finish projects. So next step really is to get it into the FT818 and then measure the distortion of my actual FT818 at various microphone levels and output powers. So I'm hoping to be able to either use spectrum analyzer I have access to at work, or potentially the club has a very good spectrum analyzer too, so I may be able to come in and use that. So that's the next step, and then it'll be on to designing the 6 metre amplifier, which hopefully will be the topic of a presentation sometime in the future. So throughout the article there's a few references. I've included them here for anyone that wants to go and check those out. Please go and have a look. And I guess I wanted to acknowledge too, I came across this presentation up here by Larry Levy on transistor and amplifier modelling methods for microwave design. And I came across this completely by accident while looking for something else, but it had some inspiring shots and a few concepts I thought would be useful for this presentation. So I wanted to acknowledge that. Thank you.
A presentation.
Cheers.
Good.
Thanks.
And thanks very much. I hope we can get this published on the website.
Yeah.
So that people can have a close look at those references, which could be very useful.
Yeah, and please come up and have a look at the board too. Please don't pick it up because it's not mounted nicely, it's fragile. In fact, I broke a wire getting it here, so more than welcome to have a look, but please don't lift it up.
Great.